My name is Malik. I'd like to thank the organizers for letting me talk. And today I'll be talking about the proof of the quantum non-energy conditions for free fermionic field theories. So first, a little bit of introduction and motivation, and then I'll move on to the proof of QNEC, or quantum null-energy condition. So the classical focusing theorem states that the expansion parameter for null geodesics is non-increasing. So we have our expansion parameter theta, and the derivative null direction is less than or equal to 0. So here our lambda is the affine parameter. The expansion parameter is a measure of how much a congruence or family of world lines expands in the future. This classical focusing theorem assumes the null energy condition, which is a local energy condition, which I'll be talking about a little bit more in the future slides. But this null energy condition is expected to be violated when quantum effects are added. So for example, if we think about a black hole radiating due to Hawking radiation, then the null energy is expected to be less than 0 or to be violated around the black hole. And so in this case, the classical focusing theorem also doesn't hold. And so Bousseau and collaborators considered a new conjecture, sort of a quantum generalization of this focusing theorem, the quantum focusing conjecture. And to sort of see where this comes from, let's look at the expansion parameter a little bit more closely. So here I have in brackets the expansion parameter, the classical expansion parameter, where A is our infinitesimal area elements. So if you look at the diagram here, A is the transverse infinitesimal area element. Any expression involving A from now on should be understood in the limit as A tends to 0. So it's known, if you're thinking about black holes, when quantum effects are added, the black hole, the area law is superseded by the second law of generalized entropy, which involves this generalized entropy here. And so Bousseau and collaborators considered doing something similar. So they they considered substituting A in the numerator with S generalized, and they conjectured that instead of the classical expansion parameter being non-increasing, this quantum expansion parameter is non-increasing instead. So the derivative of this quantum expansion parameter is conjectured to be less than or equal to 0. So what is this S generalized? So first one needs to pick a code 2-dimensional surface, which I've labeled sigma, and such that it partitions a Cauchy surface into 2. And one picks one of these partitions arbitrarily to be the out surface. So here I've got my yellow region as the out surface. I notice the boundary of this yellow surface is sigma here. so the boundary is sigma. So S generalized, which only depends on our choice of code dimensional 2 surface sigma, is equal to our entanglement entropy on the yellow surface plus the surface area of sigma. So this S out entanglement entropy is also the von Neumann entropy of our state, with the state restricted on our yellow surface. So this typically involves taking the partial trace on the other partition. So recall we have 2 surface partitions, our Cauchy surface, into 2. So this state restricted onto the out surface. So let's look at the quantum focusing conjecture a little bit more closely. So if we take let's look at this more closely. So if you look at the quantum expansion parameter, this is equal to the classical expansion parameter plus a quantum component. So this dash is the derivative with respect to lambda. And if we take another derivative of this, the quantum focusing conjecture can be reduced to saying that can be reduced to equation 4, so 0 is greater or equal to, again, a classical component plus a quantum component. And by Roche-Rodriguez equation, this classical part can be rewritten as this term here, where sigma is the shear tensor, T is the energy momentum tensor, and K is the null tangent vector, tangent to the null surface about which we consider deformations or consider our derivative. So let's go back to the previous slide quickly. So in this example, we're considering derivatives along this direction here on this null hypersurface n. N should be perpendicular to sigma. And so in this case, K would be in the null vector parallel to our normal surface n. So a few things to note here is that the derivatives of S out, so single and double derivatives, I forgot to include the double derivatives, both of them scales linearly with A. So in particular, this term here is well defined. So recall any expression involving A should be understood in the limit as A tends to 0. So this last term here is well defined. We can also choose, just by a careful choice of sigma, we can choose sigma and theta to be 0 at the point P. Point P is the, again, going back to our previous slide, point P is the point where we consider the derivatives of perturbations. So if we set our sigma and theta to be equal to 0, then this term would go to 0, this term would vanish, and this term would vanish. One can rearrange equation 4, put this term on the left-hand side, and so after rearranging, this quantum focusing conjecture implies new inequality, this quantum null energy condition. So equation 5. So we have that this is the null energy at point P. So this is evaluated at point P. So this null energy is greater or equal to some constant time the second derivative of S out, or entanglement entropy, again on the yellow surface. So classically, the null energy condition states that this term on the left-hand side of equation 5 is equal to 0, or is greater or equal to 0. But when quantum effects are added, this is expected to be violated generically. However, this has been conjectured based on this quantum focusing conjecture that this quantum null energy condition is superseded by this equation 5, the quantum null energy condition. So I'm going to call the quantum null energy condition QNEC from now on, just to save time. So just explicitly, this is what QNEC states in equation 6. So just to explain a little bit more about what this sigma of lambda means, we're going back to our surface here. So we only want to consider perturbations about our initial point P, where we want to take the derivatives. So what this means is for a different perturbation in lambda, it's considering deformations in the following form. So just deformations in the neighborhood of point P. And so in particular, if this surface has a height lambda, then we can call this surface sigma of lambda. And in this way, we can call our initial surface sigma naught. So this QNEC has been proved in some cases, in some holographic cases, in other cases. However, we've recently proven it for free fermionic field theories, which is what I'll be talking about for the rest of the talk. So in principle, for QNEC, one can choose any Cauchy surface which contains the surface sigma. So remember, sigma, co-2-dimensional surface, just needs to partition a Cauchy surface into 2. However, we'll restrict our proof to stationary null surfaces n. Stationary meaning that classical expansion parameter is 0 everywhere on n. We make this assumption for simplicity. So this can be obtained as a limit of Cauchy surfaces. So this stationary null surface n can be obtained as a limit of Cauchy surfaces. And by unitary invariance, S out on both of these surfaces is the same. So what I'm saying here is that the entanglement entropy on the yellow surface here with boundary sigma is the same as S out on a null surface n to the future of sigma. The reason they're the same is because both of these surfaces, the yellow and this surface to the future of sigma on n, have the same boundary sigma. And so by unitary invariance, one can show that these two must have the same entanglement entropy. And so what this means is that the choice of Cauchy surface doesn't change as generalized or the entanglement entropy. And so instead of choosing a Cauchy surface, we take a limit of these Cauchy surfaces and instead consider the proof on the null surface n. And so first thing we do is discretize our null surface in the transverse direction. And so we have these transverse regions, which we're going to call pencils, and we'll give these we'll give them transverse area A, which this A is going to we're going to take the limits A tends to 0, and this dark green region contains the point P. So we'll call this dark green region the distinguished pencil. This is the pencil about which we will consider our deformations of sigma. So recall, we only want to consider deformations about the neighborhood of P. We can now quantize our free fermionic field theory on this discretized null surface. This might seem a bit strange since typically one considers quantizing on a Cauchy surface. However, it turns out one can actually quantize on a stationary null surface as well, which is why we made the assumption of a stationary null surface. If one does this, our theory decomposes into multiple copies of 1+1 fermionic CFTs. These copies are disjoint, free and disjoint. And if we do this, it turns out a vacuum state vectorizes with respect to this pencil decomposition. So what I'm saying is here is that a vacuum state on n is equal to the tensor product of the vacuum state on these pencils. And so in particular, each pencil has an associated creation and annihilation operator. All right, so now that we've got our state, so now that we've quantized on our surface, how do we construct our state? Without loss of generality, we can actually just consider one copy 1+1 fermionic CFT, just because they're all disjoint anyway. And so to construct a state on the whole of n, we can Wick rotate and consider a path integral on the Euclidean plane, and to find the path integral and the vacuum state on the whole of n corresponds to inserting a branch cut along the x-axis on the whole of the x-axis, and we wouldn't have this operator insertion for the vacuum state. And so formally, the path integral is given by this expression here. But if we want to consider our state restricted to the future of sigma, so to the future of sigma, i.e. this region here, we need to take the partial trace to the past of sigma. And this corresponds to taking, by introducing a branch point. So we consider a branch point finite in the negative direction. So we have a branch point. So for sigma naught, our branch point would be at the origin. However, as we deform our sigma to the future of n, then our branch point moves along the x-axis. So different perturbations on sigma corresponds to moving our branch point along the x direction. And if you want to consider single particle states on our distinguished pencil, this corresponds to inserting a single fermionic operator in the path integral, or operator insertion in the path integral. All right, so after doing the path integral, after some computations, one finds that we can write our state in the following way. So from now on, I'm going to call this distinguished potential just a pencil, and everything else to auxiliary system. So we have a vacuum state on the pencil, restricted to future of sigma. So this is typically a mixed density state. Tensor product with our auxiliary system, plus a term to half order in A, where up to this order we have single particle states on the pencil times a Grassmann odd operator for the auxiliary system. So this sum here, we just want to sum over all the sum over a basis of these Grassmann odd operators on the auxiliary system. F is some arbitrary function, and here r and theta, we have r and theta here because I've changed from Cartesian to polar coordinates. I'm going to call this whole expression here O. So here I'm going to call this O, and here K is just the modular Hamiltonian, typically defined as logarithm of the state. So K total is just the sum of the modular Hamiltonians. So it turns out, without loss of generality, this is the most general state we need to consider, because higher order terms corresponds to more than single particle states. So to two more particle states on the pencil. That corresponds to high order terms at A, but when we take the limits A tends to 0, those terms actually drop out, so we can ignore them without loss of generality. So the way to see that this term here corresponds to the single particle states on the pencil is to note that this fermionic operator, this is our fermionic operator from our free field theory, contains a single copy of our creation operator. And this state has been constructed carefully to ensure that it's Grassmann even and Hermitian. All right, so now that we've got our state, we can now move on to evaluating the second derivative of S out. So sigma is just this whole expression here, so 10 proportional to A to the half. And so if we expand our entanglement entropy in sigma, we have that S out can be written as the 0th linear second order term plus linear and quadratic term plus high order terms. These high order terms we can ignore because they drop out again in the proof when A tends to 0. And if you consider the second derivative of S0 plus the linear order term with respect to lambda, it turns out this is equal to some constant times the null energy. So this here is the null energy, so this is equal to this term here. So I don't have time to give a general proof or to show you exactly where equation 11 comes from. But as a sort of heuristic way to see how the null energy comes in, recall that our entanglement entropy involves taking the logarithm of S out. If I go back quickly. So entanglement entropy involves the logarithm of S out. And this expression is actually known to be equal to the 1 plus 1, to the Rindler density operator for the 1 plus 1 CFT on the pencil. So at least heuristically, one can maybe see how this null energy from equation 12 enters into equation 11. And so if we now focus on equation 13 and look on the left-hand side, so we can substitute the null energy for equation 11. So just substituting the null energy in equation 11, and then simplifying, and we find that left-hand side is equal to some constant times the second derivative of the quadratic part of entanglement entropy. And so using equation 13, one can show that to prove QNEC, it is sufficient to show that the derivative second order term is less than or equal to 0. The reason is QNEC can be written in the following way. So QNEC is equivalent to this expression I've just underlined here. And so this shows the equation 14 shows that it is sufficient to prove, just to show that second derivative of S2 is less than or equal to 0. We used the replica trick to evaluate our entanglement entropy, and we just pick out the quadratic component of the entanglement entropy. So this involves analytically continuing in N and evaluating the trace for different powers of our state. And so the important thing
we are slowly running out of time. If you could finish in the next 5 minutes.
Yes, I'm almost done. Just a few more minutes. I'm almost done.
Absolutely, no worries.
And so the important thing to notice here is that S2 involves taking the expectation value of some operators related to our state on an n-replicated manifold. So, for example, this is an example of a 3-replicated manifold with various segments identified. So here, this involves 3 copies of our Euclidean plane. So the colored components are identified. So, for example, if I go around this curve here, I'll go into the blue region at the bottom surface, but come out the above surface. And so this path integral here, which we need to evaluate for the entanglement entropy, corresponds to the trace of our state to the power of 3, because n is equal to 3 in this case. And if you want to include the single particle states, that involves inserting our operator O on each of these replicated manifolds. And I don't have time to go through the calculations here, but it's not particularly insightful, just a bit long and involves quite a bit of calculations. But the point is here, we managed to find an explicit form for the second derivative of S2, which indeed is less than or equal to 0. And so this actually proves QNEC, because recall this was sufficient, this condition was sufficient to prove QNEC. And so here's a quick conclusion or summary, should I say. So the important thing to note here really is that we've reduced the problem of QNEC to show this inequality. So this vastly simplified our calculations. And so there's some future prospects. Maybe I'll go through this quickly due to lack of time. So perhaps we can find a more general proof of QNEC. Maybe other local energy conditions like the weak or strong energy condition can be considered. And perhaps this trick of substituting A for S generalized can be used for other applications or other results in GR. I'd like to thank various friends and colleagues for helpful discussions and helpful comments and discussions. I'd also like to thank the Department of Physics and Astronomy at UTSA. Thank you, and any questions?
Thank you very much. Are there any questions or comments? So if not, I have a question. I wonder which energy condition is the most troublesome from a mathematical perspective?
What do you mean most troublesome?
Let's say that it's hardest to deal with it mathematically. I mean, from physics perspective, we always try to just pray that we are in the wrong regime short enough that nothing horrible will happen.
So I guess in that sense, the stronger the energy condition, the harder it is to deal with. So I guess focusing more about these quantum generalizations, the energy condition that is a local energy condition. So for example, the null energy condition, which I'll just rewrite again, mu u k. This is a sort of point-wise condition, so it only depends on a neighborhood of a point. These sort of conditions are probably the most troublesome when trying to generalize to the quantum regime. Whereas I guess the energy condition that involves integrating over a surface or some sort of average, they're generally more easier to deal with.
Awesome, thank you. Are there any more questions or comments? If not, then let's thank speaker and see you guys tomorrow then.